This meeting is being recorded.
Am I audible?
Yes, I can hear.
Okay. Welcome to the speaker, Dr. Swagata Mandal, my colleague and students. So in this beautiful late afternoon, we'll have joined for a weekly webinar, which will be presented by Dr. Mandal, titled Embedded System Design, a System on Chip Perspective. So Dr. Mandal at present an assistant professor in Jalpaiguri Government Engineering College in West Bengal, and he has Bengal University of Technology in 2011. Master of Engineering degree on Electronics and Telecommunication Engineering from Indian Institute of Engineering Science and Technology, Shibpur, Howrah, India in 2013. And he has done his doctoral research on development of FPGA-based error recycle and self-triggered readout chain for CVM experiment at Variable Energy Circuit Center, Kolkata from 2013 to 2017. He is a postdoctoral fellow at the School of Computer Science, Engineering and Technology University, Singapore during 2017 to 2018. He is the recipient of the DGFS PhD fellowship for pursuing PhD in the area of engineering science from the Department of Atomic Energy, Government of India in 2013. And he had received fellowship for different prestigious conferences like VLSID, ATS, ISVLSI for presenting the paper. And his research interest area are in memory computation, VLSI design, embedded system design, and hardware cryptography. So now a short presentation on our university. After that, Professor Mandal will start today's session. Thank you. Professor Mandal, please start.
Okay. Thank you, Swagata. So now shall I share my screen?
Yes, sir.
Is it my screen is visible?
Yes, sir. Is it visible, sir?
So now, so very good afternoon to all of the faculty colleagues, my colleagues present here and my students. So I am Dr. Swagata Mandal, Assistant Professor in the Department of Electronics and Communication Engineering, Jalpaiguri Government Engineering College in West Bengal. So today I am going to be give a brief presentation on the embedded system design, system on chip perspectives. So first we come to the what is embedded systems. So embedded means something that is attached to another things. An embedded system can be thought of as a computer hardware that is having both software and hardware embedded on it. So combination of hardware and software designed to perform a specific function. So it is a combination of both hardware and software. It can be an independent system or it can be a part of a large system. The system can be programmable or have a fixed functionality. Means you can reprogram as per your requirement. That can be possible, or it have a fixed functionality. So an embedded system is specialized computing system that is optimized to carry out a single or very few dedicated functions. So what are the basic architecture of the embedded systems? So it consists of some sensors. That sensors basically capture the data from the environment and it converts, because you know that from environment whatever we receive, it is basically a mechanical or you can say it is a physical signal. So it can be from the, you can receive the signal from the biomedical domain, you can receive the signal from the soil, it can be from the air, anything. And the objective of the sensor is to convert the signal
Sir,
into electrical.
just
Hello.
one interrupt, sir. Actually,
Yes.
we to entire screen.
Entire screen, my screen is not visible.
Not actually, this is visible.
But
You
so
should
what I will do? It is
actually you should,
I am running in the PPT mode.
yes, PPT mode. Then you entire screen. Just select the
Okay.
entire screen.
Okay. Oh, wait. Uh, wait. So I'm just now stopping the stop sharing and then again share. Okay.
Yes, yes, yes.
Okay. Okay. Entire screen. Now it is okay. I'm selecting entire screen.
Okay,
Is it
sir.
okay now? Now it
Okay,
is okay.
okay, okay,
So
sir. Okay,
now I'm
fine.
going into the PPT mode. Now it is okay, na?
Okay, sir.
Okay. So now I'm continuing. Okay. So so what the sensor is doing, basically they convert the received signal in the mechanical or whatever in the different format to electrical signal, which can then be read by an embedded system engineer on an electronic instruments. A sensor stores the measured quantity to the memory and then come to A to T converter, because we know whenever we receive the analog signal we can't do anything with the analog signal until and unless we processed it and convert it into the digital format. So before processing we have to convert it into digital format, otherwise we can do nothing. So obviously an analog to digital converter is required that converts the analog signals sent by the sensor into the digital signal. Then processing element, it assess the data to measure the output and store it into the memory. Then D to a converter. So after the processing, now you have to display the result or processed data. So that will be done by digital to analog converter. The digital to analog converter changes the digital data fed by the processor to analog data. And now if that analog signal will need to move or need to feed to or drive any systems, then we need actuator that compares the output signal given by D to a converter to actual output stored and stores the approved output. So these are the basic architecture of the embedded systems. any embedded system. So obviously there is a processor on it, and I think my cursor is visible. So whatever I can point on the screen, you can see. So this is the processor, and the memory controller in between the bus is there, system bus is there, and along with this some peripheral device like peripheral component like sensors or whatever memory, all IO device will be there. That for that there is a peripheral bus will be there, and in between the system bus and peripheral bus, there's a bridge will be there. So in most of the cases, that may be different bus or maybe a same bus. Now, application embedded systems can be applied. We know that embedded systems starting from our one small light into our room to big into the aeroplane or in the fighter jet plane or ballistic missile. Everywhere embedded systems are used. So there is a all over the field the applications of the embedded systems are there. So some of them are automotive industry, military application, healthcare or biomedical, telecommunication, banking industry. In the banking industry, you can take an example like an ATM machine. This is one example of the embedded systems. Different household applications like your remote sensors, like remote control to switch on or off your TV. This is an one application of the embedded systems. Some home automation and security applications, consumer electronics, etc. So these are the basic architecture of the embedded systems. So with the heart of this embedded system, as we mentioned, that CPU or processing unit will be the heart of the embedded system. Some storage element like SRAM, static RAM or SD RAM will be there. Power supply will be there that will drive whole the systems in order to communicate that whole system to external world. Some communicating media like Ethernet, MAC, UART, these will be there. And apart from this clock module that will drive the whole systems, and some custom logics will be there that will help to help to process the data. And apart from the required some kind of co-processor like I will discuss couple of slide later that GPU or NPU will be there as a co-processor. Okay. Or sometimes some hard macro or IC will be like audio codec, timer, this will be there. Today, silicon technology allows us to build chips consisting of hundreds of millions of transistors. This technology has enabled new level of system integration onto a single chip. This is a very interesting thing that nowadays technology reached to such a level that it integrates whole systems into a single chip. So demand for more powerful products and the huge capacity of today's silicon technology for emergence of system on chip technology. So SOC or system on chip technology responsible for maximum amount of technology into a smallest possible space. That is compact whole system into a single chip. So complex, what is system on chip? A complex integrated circuit or IC that integrates major functional elements into a single chip. In addition to IC, SOC consists of software and connection structure for integration, may contain digital, analog, mixed signal functions in a single chip substrate. The components of SoC include CPU, GPU, memory, or IO devices, etc. Compared to a multi-chip architecture, and SoC with equivalent functionality will have increased performance and reduce the power consumption as well as smaller semiconductor die area. So basically, it compared to multi-chip means when I will see later, a couple of slides later, that uh, you can perform the same functionality on using the different component on the breadboard or your PCB, but difference is that it has to be the separate component. What are here SoC, they provide the equivalent functionality, but it increase the performance with the reduced power consumption and the smaller semiconductor on the same smaller semiconductor area. Due to their low power consumption, SoCs are very common in the mobile electronics market and finds a wide application or wide use in the arena of embedded systems. So these are the basic architecture of the SoC. You see that it is quite similar to the embedded system architecture, but the difference is that whole systems, my whole this background, this whole system on the single silicon wafer. So these are the core, CPU core, DSP core will be there. Um, some user defined macro core can be there, some third party core like some from the other uh, company can provide the core. This memory element will be there, and to communicate with the IO or to communicate with the external environment or external component, the IO pads, IO periphery will be there. Okay, but all these on the are on the single semiconductor wafer. So these are the SOC component on the same wafer. So this is one single silicon area. On this single silicon area, these are the MPEG core. Just one example I have taken. Main is the CPU, obviously. Some for particular signal processing unit, DSP will be there. For external communication, there is the analog RF component will be there. GPU for the graphics process, for graphical processing unit, for GPU for high performance computing is there. For video or audio processing, MPEG core will be can be there. So these are the one example. But apart from this, some other components can also be incorporated onto the single silicon wafer. So I have taken one example like Samsung S3 S3C6410 platform. This is one example of the SoC. What? So here you see there's ARM core will be there. ARM core is there, and this ARM core along with this ARM core, these are the CPU architecture. So along with this, as some peripherals like DMA, watchdog timer, RTC will be there to communicate with the external world. GPIO, UART, then MMC, USB, these are there. For multimedia like video, audio, video, image processing, codec, JPEG codec, graphics unit will be there, and this memory unit that SDRAM, DDR, NAND flash that can be there. So and for power management, LDO, CMOS, this will be there, and for display TFT LCD. Sometimes instead of TFT LCD, there is a you can see this OLED can be there. Okay, and these are the bus architecture. These are the bus. This AXI or advanced microcontroller bus architecture or AXI bus will be there. And when this communication will be done from the processor to IO device, that data will be transferred to the bus. To secure that data transfer, there's a crypto engine is there. So this is one example of the SoC, because all are on the same platform. So these are the what I have just mentioned, that it is consists of 16 to or 32-bit disk processor. This can be applied in mobile phone, portable navigation device. Okay, and it is used for the 2.5G and 3G communication. And this includes many powerful hardware accelerator for motion video processing, and for display TFT 24-bit LCD controller power management. These are there. So these are the two application where these uh, SoC are used. One navigation system, one iPhone where this is used. Now another example of the Samsung S5 PC100 SoC. You see here it is also ARM processor, where it is newer version of the ARM processor. There is ARM Cortex A2 A8. This is a multi-core ARM processor will be there. Okay. So these are the has various functionality, like for wireless communication it is used, personal navigation, camera were used, for portable gaming, video player, mobile TV, all will be included on the same device. It is a 32-bit ARM A8 Cortex microprocessor and operate at the 833 megahertz. It is a internal bus architecture is either 64-bit or 32-bit wide, and it is used iPhone 3G and iPod such Touch third generation. Okay, so these are the basic architecture of this S5 PC100 AC. So these are the processor, and along with this, there's one interesting part. One cache memory is there, L2 cache, and along with the neon processor. This is basically used for floating point processing. Okay, floating point processing. Otherwise, all are quite similar to the previous one. Now MPSoC. What is MPSoC? So MPSoC is multi-processor system on a chip. It is a system on chip, and it contains multiple instruction set processor. Means on the same chip, multi-core processor will be there. Instead of the single core, multi-core processor will be there. And a typical MPSoC is a heterogeneous architecture where several different types of processing unit is there. So what does it mean? That multi-core in that sense that either same type of processor, maybe they are like four same processor will be there, four same type of processor, or that then that will be homogeneous multiprocessor. And case of a heterogeneous multiprocessor, four different type or two different type of processor are integrated on the same chip, then it is called heterogeneous multiprocessor. The memory system may also be heterogeneously distributed around a machine, and the interconnection structure between the processing element, the memory may be also heterogeneous. Memory may be either homogeneous or heterogeneous, means either same type of memory or different type of memory. So MPSoC have large memory. The application device can have embedded memory on chip and may rely on off-chip commodity memory. Means suppose I have a memory chip on the memory that is suppose 64 MB memory or 2 GB memory, but you can extend, because most probably when we go for purchasing the mobile, it says that it is a 4 GB memory. You can extend up to 32 GB, means another 28 GB you can attach for externally. So one example of the multi-core processor, that is SC2A11, a multi-core processor associated with 24 core instead of the single core, just whatever we discussed previously. This is ARM Cortex A53. That was ARM Cortex 8. It is ARM Cortex 53. SC2A11 is suitable for low power server systems. It can also suit for edge computing to process the data at the edge of the cloud. So you see, these are the SC2A11 based transcoder system. Means during the transcoder system, means when for high performance video and video processing will be done on this SC2A11 platform. So high energy efficiency processor element is realized with multi-core configuration or ARM Cortex A53, and large amount of video data can be processed in faster. Why? Because multiple core can process the data in parallel. So you see that multiple core process the data in parallel. So that's why it is quite faster compared to single core. Now traditionally we know that uh, suppose when we have to design something and we have to send it to the field, in general ASIC will be used. In general, still now ASIC is used. What is ASIC? ASIC means application specific integrated circuit. Means you design the chip for a particular application and it will be that part application only. You can't change it. But the difference between ASIC and SOC will be like that. This application specific integrated circuit is quite close to SOC design to perform a specific function for the embedded and other application. But ASIC vendors supply the library to for each technology they provide. Mostly this library contains pre-designed or verified logic structure. But SOC is an IC designed by combining multiple standalone VLSI design to provide functionality of the IC for an application. Means you assume that ASIC just library you are taken from the vendor, you fabricate it and you provide to the user. But in the SOC, you integrate standalone multiple VLSI design on the single platform, and it can be reprogrammable, reconfigurable. Okay, so it comes for a pre-designed models of complex functions like IP block, virtual components that can be there. You can use it, and that can serve various applications. So these are the ASIC design flow. If you see that ASIC design flow takes quite long time, almost 52 weeks it takes to come to the market. These are the some steps like top model design, block design, verification, physical design, schematic entry, then verification, and then fabrication, then packaging, testing, like this. So it takes almost 52 weeks to come on ASIC chip onto the market. Now, what SOC design will take? SOC, what when you design SOC design, what we need and why we opt for the SOC instead of the ASIC? Because so first, when you going to design SOC, what you want from the users? So first you have to ask the user what does they really want. Okay. So now find the most and cost and performance effective architecture to implement it, and which existing component can we adapt and reuse, means whether any IP is already there that we can reuse, then what is the performance impact of that impact of a cheaper architecture, what can we generate automatically from the library and customization, use separate communication, computation, etc. So these are the SOC design flow. You see that one SOC chip to come to the market, it takes only 28 weeks. So they compared to, you see in the previous, that is almost 52 weeks. Here it takes only 28 weeks. So very less time it takes, though design quite similar, but here the advantage is that you can reprogram, recompute on the field. It's quite similar to FPGA. I will discuss later what is the difference between FPGA and SOC, because in the FPGA, there is a FPGA or reconfigurable computing platform. You can reconfigure as per your requirement, but it is only based on some logic area. But in the SOC, difference is that your processor will be there as a normal computing system along with the FPGA or reconfigurable systems will be there. So as a whole, you can see SOC. So SOC, you can say it is a superset of the just one step above the FPGA. So it is like FPGA, it is reprogrammable, but compared to difference is that your hard quite macro will be there, which enhance its the performance like or quite similar to ASIC. But compared to ASIC, its time to market or complexity is quite less. So these are the SOC design flow. You see that though it may looks complex, but the system is architect means steps are quite same, like generic hardware IP blocks will be there, specified system on chip, generic software IP blocks. What are the IP blocks you need? Then you take it from the users, then you partition which portion. Here advantage is that you can go for the hardware software co-design. So some portion you can process on the software part, and some portion you can do on the hardware part. So you can partition, you have to partition, there is a partition that partition in the partition that this portion I will do in the hardware, this portion I will do in the software. So based on that you will perform, then implement on it on the hardware, then perform that using the test using the software input, then perform the physical design, then testing, verification, and then before that physical design you have to lay out the design. Then after that physical design is done, you have to go for the fabrication, then there is a packaging, then again testing will be there. So these are the basic steps in the SOC design. So what is the SOC market? So systems on chip market will reach at an estimated value of USD 501.8 billion by 2028. So rise in the demand of the system on chip for smartphones is an essential factor driving the SOC market. So what are the major companies that are driving the SOC markets? The Xilinx, MediaTek, Qualcomm, Broadcom, Intel, Apple, TI. These are the some of the examples. Apart from these, there are lots of companies which are now taking a leading role in the SOC market. So now we are switching from the system on board to system on chip. So system on board, as I mentioned, that we are in the lab, we are designing lots of experiment, we are perform lots of experiment using various discrete component on the breadboard. But in the SOC or system on chip, we integrate all these component on the single chip. So these are the example from the SOB to SOC. You see that everything like clock, memory, arithmetic unit, function, interface, all are on the one PCB. This is the left one. On the right one, everything is incorporated on the same chip and will provide in the one packaged. So this is called the SOC. So these are the basic SOC architecture. So that SOC may be as I mentioned, that SOC processing elements on the SOC may be homogeneous or heterogeneous. Means it may be either only CPU or CPU with different capacity, or CPU with some hardware component like FPGA or reconfigurable computing platform, which you see that these are the on the left side, on the right side is green, there's a tile of the SOC chip. So these are the switch fabric, that is the this portion, and there's a core, that is the CPU core will be there. So these all included onto the single chip. So these are the advantage, and these are some of the advantage and disadvantage of the SOC. So advantage of the SOC, that is a low power, low cost, high reliability, small form factor, high integration level, fast operation, greater design, and small size. So obviously these are the advantage. But when you go for the design, obviously along with the advantage, there are some disadvantage. So what are the disadvantages? Fabrication cost, increased complexity, time to market demands more verification, etc. Because obviously costing will be high when you go for the complex design, and complexity will increase. Time to market demand, that though time to market is less, but still it is higher than the FPGA. So time to market is high, and more verification is required. So now go for some applications. So any question, anything? Hello.
No, sir. Please
Okay, okay,
continue.
okay, okay. So okay, so some of the applications. So one of the most common application nowadays is the machine learning application and landscape. So if you see for the machine learning, now machine learning are used in every domain. That's why knowingly I have chosen that platform. So now what we are doing in basically machine learning, these are the basically you see in the left right side, there are the different industry. Though I have mentioned very small like medical or healthcare, industrial or military, oil and gas, enterprise, transportation, consumer entertainment, retail, and these every domain nowadays machine learning, or rather nowadays deep learning are used. Okay, now these machine learning means what you are do. There is a difference, mark demarcation between the machine learning and deep learning is there. In the machine learning, you have to calculate, or you have to calculate these handcrafted features and give into the system, and then based on that feature, when you give the input, the user will the system will take decision. But in the deep learning, you are directly feed to the data set, and machine itself trained themselves, and then when you give input, it will take decision. So now these can be computed in various platforms, like it can be these can be trained either on the edge, or on the cloud, or on the hybrid solutions. Okay, now nowadays in general CPU, along with now CPU is not sufficient. We know that CPU is not sufficient alone to the machine learning application, machine learning or deep learning. Just when you increase the data, your computing system becomes are not able to support it. So that's why you go for the GPU. Now CPU along with GPU is okay, but the problem is that CPU and GPU, when you go main issue is the GPU is that it cannot be run on the, first of all, its complexity, cost, and not cost is not as issue, but power consumption. And most problem, most one of the most problem of the GPU is that it can't run on the standalone mode. But when you go for the SOC platform, SOC based architecture, SOC can be run on the standalone mode. And another advantage of the SOC is that here you can get the flavor of everything on the same package. Like on the same package, you can get CPU, you can get FPGA as an accelerator, and nowadays along with the CPU, FPGA, there is a GPU is also coming, that is called neuron processing unit, that can also be incorporated. So all are everything coming in the stand, means on the single chip, and that can be run on the same on the standalone mode without any host processor, like GPU, unlike GPU. So these are the advantage of the advantage of the SOC compared to normal traditional computing systems. So I have taken this ML application. So apart from the ML, there's a lots of application where this SOC overcome some of the some of the traditional computing platform. So you see that. These are the base, some of the computing platform like so in the machine learning, there's a two part. One is the training part, and one is the inferencing part. Training part, in the training, we are mainly use the high end computing, because there is a lots of data are used for the training during the building the model. And during the testing purpose or inferencing purpose, you can use, maybe there is a less computing resource are required. But this SOC architecture can be used in every part, like in the training, inferencing, and replacing all these architecture. So now I am coming just one example, one common SOC example of the Xilinx. There's a ping platform. One is called ping platform. This ping platform can be used for the SOC application. This ping platform can be used for the one of the SOC example. Ping is one of the SOC example. Ping means Python 11 Zinc. So before that, I am just, though there is no such slide, but still I am discussing one what is Zinc. Zinc is one example of the SOC from the Xilinx. It is a basically SOC developed by Xilinx. Apart from the Xilinx, there is another example, Altera, one company that is acquired by Intel. It has also one SOC, other SOC platform, but Xilinx is one of the leading vendor for the SOC, and Zinc is one of the standard SOC developed by Xilinx. But nowadays you see that for the machine learning application, Python is quite common. Python is quite common for the machine learning application. All students, faculty member, they are using the Python for the analysis. So that's why when they are using this Python, so then the company come up with that, okay, how to integrate that Zinc with the Python. So that's why the name came Python enabled Zinc platform. So what is the Zinc? Zinc, you see in the right side, you see that these are on the left side, these are the traditional SOC architecture. In the DSP or GPU units are there. Sensor, all data are coming from the sensors. These are the CPU where the processors are there, and along with some mobile IP, that is a motor control IP will be there that will control the data. But here you see that every data is coming onto the DDR RAM, external RAM. Okay, like for image, ultrasonic, radar, IMU, all data are coming to the radar, DDR RAM, and from the RAM you are capturing the data. But what the Zinc platform provides, in the Zinc platform, every data from every sensor like the image, ultrasonic, radar, IMU, every data from the every sensors coming onto the directly on the processing unit instead of the separate DDR. DDR is here separately for the storage, but not this data is coming to the DDR. So that's why your communication time or latency is reduced. Then the every processing are the same, but difference you see that the Zinc platform and normal typical SOC is like that. Now these Zinc SOC basically, Zinc platform is that there is a CPU, that part we will do. These are the CPU part, and where you this RAM and everything is connected, and the sensor data is coming into a programmable logic unit or FPGA, where these various kind of the acceleration and computation will be done on the programmable logic. So now when the CPU comes on the CPU, various operating systems will run. Operating system means like operating systems here can be used in the Linux kernel. Linux means these Peta Linux, Femto Linux. These are the Linux kernel will be there. On the Linux platform, the Python of Linux Python can be run, or apart from this Python, there is a lots of nowadays it supports the various kind of machine learning library like Keras, R, Cafe, like that. So all will be run on this CPU. That will, so what the programmable logic will do now, these processor system or these data, these OS system basically, when the computation is required, which is basically in highly computationally intensive portion, that will be basically pushed into the programmable logic portion, where these data will be processed in parallel. That is quite similar to the GPU architecture, where that is in parallel it can be done. And after the processing data will be pushed back or given back to the CPU, that will be displayed through, or it can be sent to other external device. And the tools for these high level, this can be done either these programmable logic can be controlled normal Verilog code, or it can be done through high level synthesis called SDSOC or Vivado HLS, and it is run. These logic can be programmed. There is the EDA tools called Vivado HLS, which can be code using standard or normal C++ library. And this ping framework basically enable the Python to work on the Zinc portfolio, that will basically control control whatever logic you have developed using either C, C++ or Verilog and placed onto this programmable logic. There is a misconception that means pink means if you know Python, you can run the program this SOC. It's not like that. Hardware logic or programmable logic that you have to develop this IP core, or you have to or you can use various predefined IP core that will be still developed using either Vivado HLS, which is controlled by C, C++ or Verilog code. But when you control that logic, that can be done using Python. That's why it is called ping. So these are the ping platform in more elaborate way. So when you get ping is the first framework to combine the following element: a high level productivity language, that is the Python. Nowadays, instead of the Python, as I mentioned, these Keras, R, and various language will be there. So various hybrid library which enable the acceleration in PL. That is very interesting thing. Very hybrid library which enable the acceleration in PL. A web-based architecture served for the embedded processors, Jupyter Notebook framework, all are integrated on the same platforms. Okay. So these are the application in ping platform. You see that here the ping architecture is there, and these are the all are integrated like SymPy, ROS, NumPy, scikit-learn, pandas for the data analytics, sensors, robots, and everything all are integrated on the same platform. So now these are provided. This ping basically provide your hardware. Not only ping, basically SOC itself provide hardware software co-design. So what is the hardware software co-design? Hardware software co-design means the advantage is there here is that you can separate your design in such a way that you can segregate that which portion of your design can be run on the hardware or which portion of your design in run using the software platform. So you see that one is the FPGA portion, or so when you program this FPGA portion using the bit streams logic, that will be controlled using these are the placed on the hardware part. And now this is the Jupyter Notebook or the OS part on which the Python is running. So in between the AXI interface is there, basically that will control. So on sitting on the OS portion or on the PS section, you control your FPGA or logic section. Okay. So some of the example, one example is the image and video processing examples. So you see that here there's a these are the application of Simulink HDL coder. Using that, you basically, so how when you do design any image or video processing application, how you perform the design? First you have to test the data, test the language or test the code on the MATLAB or C++, whatever. And if you go for the MATLAB, then the MATLAB, when the performance is okay, then there is a HDL coder is there. That HDL coder will generate automatic this RTL code or RTL code that is converted into the IP core. That IP core will be dumped into the programmable logic unit, and there is a separate portion on the SOC. There is a processing as the ARM processor is there along with the memory unit. So on the top of this application software will running on will run, and there is an interconnection between this programmable logic and ARM processor. There's an interconnection. This is AXI interconnection. AXI full form is the this advanced microcontroller bus architecture, extended bus architecture, that is called AMBA bus also. That is a specific this is a communication between this PS and PL portion. And because when you go for the image and video processing, why this kind of design is needed? Because video and image processing, there is a lots of parallelism and very data intensive computation is required, where inherent parallelism in parallel computation is very needed, very much needed. That's why you see that lots of application acceleration blocks are on the programmable logic which run in parallel. Okay. So you see there's a one example design where this is the JC104 Zinc board, and one camera module is attached to it. That camera will directly receive the data, and already we have trained the one model of the ResNet onto the systems, and that is this model will be already trained, and this trained model are placed on the programmable logic area, where this data, where this camera captured the data and received the data and transferred to the PS, and from the PS it is going into the PL, where the inferencing is done for the various application, the detection, classification, like that. Now, similar way, there is a, it can be used for the biomedical application. Biomedical signal processing applications will be there. So one example here is that ECG data processing for arrhythmia detection. So first there is a pre-processing data. Pre-processing will be there, means after receiving the data, you have to remove the noise, you have to filtering the noise. There's a DC balancing will be there. So these kind of pre-processing will be there. So after that, various statistical analysis like mean, media, mode, there is a energy, various features will be calculated from it, and then you have to train using the, what we have done basically here, we have trained and prepare a model using the support vector machine, and that support vector machine will run, training is still done on the GPU, and after that inference engine will, after the training, that trained model will be placed on the on the FPGA on this programmable logic area. And now after that, when you receive an ECG signal, you directly put it into the feed into the SOC, and this from the processor, that received signal will be transferred to the PL section, where data analysis or inferencing will be done, that that from that signal we will decide whether there is a arrhythmia present on the patient from which we have received the data, or if arrhythmia present, what kind of arrhythmia, because there is a various type of arrhythmia will be there. Now another example, there's IoT. There's a lots of application of the nowadays coming with the IoT. IoT is basically nothing but various sensors integrated with the internet, and which capture the data and transfer to the cloud, where basically various analysis will be done. So these are the IoT stacks. You see the device communication layer, because device will capture the data, then communication layer will receive the data and send to the some cloud or fog, and fog will be sent to the cloud, where various analysis application will be there. From there you mm, perform various kind of decision making application will be run on the there, and from there it will coming back to the sensor level. Okay, so these various applications, or these various applications labels will be, can be computed using the, or can be implemented using the SOC. So you see that this is the communications in IoT. So there is a communication, means that either device to device communication can be there, or directly device to the backward, like gateway, Wi-Fi, and then IoT platforms. But these everything can be formed or implemented using the SOC. Okay. So one very common example, SOC based IoT network for different application. You see that there is a agriculture, smart agriculture, retail, health, power, smart homes, automation, environment monitoring, smart city, intelligent transportation, infrastructure monitoring. Everywhere we can use the SOC based architecture. Okay. So some of the reference from where I have prepared my design. So thanks everyone for hearing. So any question from the audience?
Thank you, Dr. Mandal. Now we will take some time for question. So any question? Okay. Sir, I have two questions. First,
Okay,
what is
sure.
the basic difference between the SOC and ASIC? That is the first question.
Okay.
And second question, what is the basic difference between the FPGA and ASIC?
Okay. So first of all, SOC and ASIC, what I have mentioned, that ASIC means application specific integrated circuit. Okay. So whenever
Yes.
you will design any chip for a particular application, it is one time. You have designed and then you have to send to your customer. And if it is whatever is there, means whether it can be performed well or not, if there is any problem, or if you want to reprogram, you can't do it. Okay. This is the ASIC.
Okay.
And then it is coming to the FPGA. FPGA means it is the field programmable gate array. Means you can reprogram as per your requirement, and at the same time you can, there is an inherent parallelism, all be included. And main thing is that on the field, if you require, suppose at I take one example, suppose now at the moment I am design one half adder, in the next phase it required, okay, now no, I want to convert it into full adder. So how you can, in the ASIC you can do, but in the APG you can do it easily. Okay, so
Okay.
because it is reprogrammable on the field, so this is the FPGA, that's why it's come this is the name, that field programmable gate array. This is the difference between ASIC and FPGA. Now on the SOC, what is the difference with the SOC? SOC is there in the FPGA or ASIC, everything is the homogeneous. Homogeneous means it is either fully logic FPGA means, and ASIC means logic, but it is the fabricated. But SOC is the two part integrated. One is your, means all are heterogeneous, means I, yes, this SOC will include CPU, like processing in normal traditional computer. Along with it, GPU will also there, FPGA will can be also there, NPU can be there, TPU can be there. Everything can be done. Everything can be there, but all are integrated on the same platform. Okay, so this is the difference between SOC and FPGA as well as SOC and ASIC. Okay.
Okay, sir. Okay. So thank you everyone. I hope that is has been a great experience for everyone. So we appreciate Professor Mandal being here, and thanks again also, and thanks again for the joining us today. And we will see you all the next week around 4 p.m. Thank you, Dr. Mandal.
Thanks. So thank you.